Comparative study of ordinary and Supa sections of cold-formed steel. Abstract cold-formed steel, CFS, is one of the types of steel which is processed by cold working procedures. It is carried out near the room temperature. They are generally used as flexural members in lightweight steel construction. They are structurally and costly effective, thus their thin-walled members are used in low and mid-rise building construction. There was a rapid growth in the usage of CFS in buildings because several innovative and structurally efficient CFS products were easily available. Their advantages include lightness, high strength and stiffness, ease of prefabrication and mass production, fast and easy erection and installation, etc. Ordinary and Supa are the two types of cold-formed steel sections. The Supa section is an innovative section introduced in Australia. It is having the specialty of unique ribbed web and curved lip elements, thus it provides superior flexural strength when compared with traditional channel sections. This paper presents the comparison of ordinary and Supa sections on the basis of performance of both the sections. C, Z, and sigma sections of both ordinary and Supa sections are numerically evaluated using buckling analysis. It was found that Supa sections were effective than the ordinary sections of cold-formed steel. Keywords: flexural members, ribbed web, curved lip. Introduction. In steel construction, there are two main families of structural members. One is the familiar group of hot-rolled shapes and members built up of plates. The other, less familiar but of growing importance, is composed by cold-formed sections from sheets, strips, plates, or flat bars in roll-forming machines, by press brake or bending brake operations. 1. These are cold-formed steel structural members. The thickness of steel sheets generally used in cold-formed steel structural members ranges from 0.5 mm to 4 mm for sheeting and from 1 mm to 8 mm for profiles, respectively. 1. Steel plates and bars as thick as 25 mm can be cold-formed successfully into structural shapes. The use of cold-formed steel members in building construction began in the 1850s in both United States and Great Britain. 1. In general, cold-formed steel structural members provide the following advantages in building construction. 1. As compared with thicker hot-rolled shapes, cold-formed light members can be manufactured for relatively light loads and slash or short spans. 2. Unusual sectional configurations can be produced economically by cold forming operations and consequently favorable strength-to-weight ratios can be obtained. Binu P. Association Professor, Department of Civil Engineering. Srinarayana Gurukulam College of Engineering. Ernakulam, Kerala, India. 3. Nestable sections can be produced, allowing for compact packaging and shipping. 4. Load-carrying panels and decks can provide useful surfaces for floor, roof, and wall construction. 5. Load-carrying panels and decks not only withstand loads normal to their surfaces, but they can also act as shear diaphragms to resist force in their own planes if they are adequately interconnected to each other and to supporting members. 1. Cold-formed steel is used as flexural members in lightweight steel construction. They are structurally and costly effective, thus their thin-walled members are used in low and mid-rise building construction. There was a rapid growth in the usage of CFS in buildings because several innovative and structurally efficient CFS products were easily available. Advantages also include lightness, high strength and stiffness, ease of prefabrication and mass production, fast and easy erection and installation, etc. Products of cold-formed steel are available in different shapes and sizes. So, it is effectively used as partition walls, roof purlins, roof trusses, floor joists. Ordinary and Supa are the two types of cold-formed steel sections. The Supa section is an innovative section introduced in Australia. It is having the specialty of unique ribbed web, crimps, and curved lip elements, thus it provides superior flexural strength when compared with traditional channel sections. This paper presents the comparison of ordinary and Supa sections on the basis of performance of both the sections. Performance can be effectively analyzed by the load carrying capacity of each section. C, Z, and sigma sections of both ordinary and Supa are taken for the analysis. That is, C, Z, and sigma sections of ordinary cold-formed steel are compared with that of Supa sections respectively. 2. Numerical analysis. Dimensions of the model and other relevant input parameters are taken from a journal to verify the accuracy of a numerical model. Finite element software is used to reciprocate the numerical analysis from the particular journal. The details were taken from Journal 5 for the validation of mathematical model using the finite element software ANSYS 16.1. The model named as ETFSC20015 was taken for the purpose of validation. The model is having ribbed web and curved lips. Section depth is taken as 204.9 mm, flange width as 69.7 mm, corner radius as 5 mm, lip width as 22.9 mm, and 12 mm stiffeners. Elastic modulus and Poisson's ratio of steel from the journal are 200,000 MPa and 0.3 respectively. Modeling of the specimen as per the journal and meshing were done using the software. Modeled specimen is loaded so that displacements and forces were obtained. Load deflection curve of the model is obtained. The web crippling capacity obtained from the journal was 3.04 knots and that obtained from FIA is 2.849 knots. Hence, the percentage error is less than 10%. Fig 1 shows the Supa section used for the validation. Fig. 3 Modeled view of Supa C. Material properties of the models were chosen from the engineering data of the ANSYS software. Pre-assigned values for each material is given in the engineering data section of the software. Table 1 shows the material properties of the model. Fig 1. Supa C section. Buckling analysis is done in this paper for all the sections of ordinary and Supa to study their performance and to identify which one is better. A modeling of ordinary and Supa sections. Numerical modeling of the ordinary C, ordinary Z, ordinary sigma, Supa C, Supa Z and Supa sigma models were performed by the FE software ANSYS 16.1 workbench. Fig 2 and 3 shows the modeled view of ordinary C and Supa C respectively. Table I Material properties of models. Material cold-formed steel. Modulus of 2x 105 N/mm2. Elasticity. Poisson's ratio 0.3. Density 7,850 kg per cubic meter. Yield strength 250 MPa. Totally 6 sections were modeled. Nomenclature for the model is given as per the presence or absence of crimps in the web and shape of the model. The models without crimps in the web were named as ordinary C, ordinary Z and ordinary sigma. The models with crimps in the web were named as Supa C, Supa Z and Supa sigma. Ordinary C and Supa C is having the shape of letter C, ordinary Z and Supa Z is having the shape of letter Z, ordinary sigma and Supa sigma is having the shape of symbol sigma. B. Support and loading. Support condition and loading was given to all the models after modeling. The fixed support was given at the bottom of the model and displacement was given at the top of the model. Fig 4 shows the Supa C model with fixed support at the base. Fig 5 and 6 shows fixed support of Supa Z and Supa sigma respectively. 6 models were obtained and among that 3 of them belongs to ordinary section which is not having crimps in their web and other 3 belongs to the Supa section which is having crimps in their web. 3 Results and discussion. Buckling analysis was done to the 6 sections such as ordinary C, ordinary Z, ordinary sigma, Supa C, Supa Z and Supa sigma. Values of total deformation and force reaction were taken from the ANSYS software and these values were used to plot the load deflection curve of all the sections. Figure 7 shows the load deflection curve of Supa C, Supa Z and Supa sigma. Figure 8 shows the load deflection graph of ordinary C, ordinary Z and ordinary sigma. Table 2 shows the maximum deformation and corresponding force reaction of all the sections. Fig 7. Load deflection graph of Supa C, Supa Z, Supa sigma. Fig 5. Supa Z model with fixed support. Fig 6. Supa Sigma model with fixed support. Buckling analysis was done to all the sections using the software ANSYS 16.1 workbench. After the analysis, the buckling behavior of all the models were obtained using the load deflection curve by taking the values from ANSYS. The performance of ordinary C is compared with Supa C, ordinary Z with Supa Z and ordinary Sigma with Supa Sigma. Load carrying capacity of each section was considered to find the best section and for comparison. Stiffness of each section is found out using total deformation, mm, and force reaction, kn. Fig 8. Load deflection graph of ordinary C, ordinary Z and ordinary Sigma. Table 2. Maximum deformation and force reaction of all sections. Section max deformation, mm, force reaction, kn. Supa C 67.6292.849. Supa Z 46.714.2269. Supa Sigma 64.5413.1266. Ordinary C 49.592.1042. Ordinary Z 26.863.2086. Ordinary Sigma 41.7642.3765. Fig 7 and 8 shows that up to a particular deformation, the value of force reaction is increasing and then decreasing for all the sections. At that point, failure is occurred. From the values of Table 2, stiffness was found to be more for the ordinary sections of cold-formed steel. But when considering the load carrying capacity, ordinary sections are less effective than the Supa sections. From the figure 7 and 8 it is evident that load carrying capacity of all the Supa sections are higher than that of the ordinary sections. On comparison of each sections it was seen that Supa C is having 35.4% more load carrying capacity than ordinary C, Supa Z is having 31.7% more load carrying capacity than ordinary Z and Supa Sigma is having 31.5% more load carrying capacity than the ordinary Sigma. Hence, the strength of all the Supa sections will be greater than that of the ordinary sections of cold-formed steel. Supa Z is found to be the best among all other sections, which is having the capacity to carry load up to 4.2269 knots. From Fig 7 it is observed that, Supa Z is having more load carrying capacity than Supa C and Supa Sigma. But when considering yielding capacity, Supa C and Supa Sigma is more effective. Similarly, from Fig 8 it is observed that, ordinary Z is having more load carrying capacity than ordinary C and ordinary Sigma. But when considering yielding capacity, ordinary C and ordinary Sigma is more effective. For conclusion. In this research, behavior of all the models were analyzed in ANSYS Workbench 16.1 using buckling analysis. Compared the performance of Supa C with ordinary C, Supa Z with ordinary Z and Supa Sigma with ordinary Sigma. Change in the properties of ordinary models were due to the absence of crimps in their web. Hence, strength of each Supa sections was greater than that of the ordinary sections. In this paper it is observed that, Supa C is having 35.4% more load carrying capacity than ordinary C, Supa Z is having 31.7% more load carrying capacity than ordinary Z and Supa Sigma is having 31.5% more load carrying capacity than the ordinary Sigma. Supa Z was found to be the best section.